11 factorial has 540 positive factors. And we can see that because 11 factorial's prime factorization is 2 to the 8th times 3 to the 4th times 5 to the power of 2 times 7 to the power of 1 times 11 to the power of 1, which you can verify if you want. Now, because it has this prime factorization, we say it has 8 choices on the power of 2 plus 1, because the power of 2 can also be 0 in any factor. So 8 plus 1 choices on the power of 2. It has 4 plus 1 choices on the power of 3, 2 plus 1 choices on the power of 5, 1 plus 1 choices on the power of 7, and 1 plus 1 choices on the power of 11. And if you calculate this out, this will come out to 540 positive divisors, or positive factors. Now, my question is, how many of these factors, satisfy the following property? Satisfy that the greatest common divisor between that specific factor and the number 396 equals 12. How many satisfy this kind of arbitrary property that they have a GCD of 12 with 396? Well, okay. The first step, always, in any of these problems is to find a way to generate your factors systematically so you can run through them and say, these factors have this property, these factors don't have this property. And in a previous video, where we found all of the factors of 11 factorial and took their sum, in that video, we went over a method that we can generate factors of 11 factorial, and really any number with its prime factorization handy. And that method was to say, take any power of 2, 2 to the a, where a is between 0 and 8, and then take any power of b, where b is between 0 and then 4, because of this 4 up here, and again the 8 is coming up from there, and then multiply by any power of 5, where this power of 5 has to be greater than 0, but also less than the power of 5 here, so less than or equal to 2. And then take your power of 7, where the power of 7 is same deal except less than 1, and then take your power of 11, and that power of 11 must be, again, greater than 0, less than 1. This here is a method for generating arbitrary factors of 11. All 540 of them can be generated from this. And now, if we were going to take this, how would we go from arbitrary factor to satisfy GCD? Okay, the first step might be to also convert these numbers to their prime factorizations. I have them on hand. If you want to check them, go ahead. 396 is 2 squared times 3 squared times 11 to the power of 1, because in essence you're going 3 squared times 11 is 99 times 4 is 396, 4 less than 400. 12 is, this one's more simple, it's just 2 squared times 3, so 4 times 3, 12. So we have these numbers. Really, what we're asking is, if we're asking for factors here, d, that satisfy this, our question is actually, how many cases are there for which the GCD of a number in the form 2 to the a, 3 to the b, 5 to the c, 7 to the d, and 11 to the e, where all of these constraints still hold, with the number 2 squared, 3 squared, times 11 to the power of 1, equals the number 2 squared times 3 to the 1. Now, in this more general form, it might be easier to start to get at the solution. But before we do that, we have to conceptualize very firmly what the GCD actually does. So let's do some examples in the prime factorization form. What is the GCD of, okay, let's start without the prime factorizations, then work up to it, 20 and 8. Well, this is equivalent to the GCD of 2 squared times 3 to the 0 times 5 to the 1, so 4 times no 3's times a 5, so 20, with the GCD of, or sorry, with the number 2 cubed, 8. We know from experience that the GCD, the greatest common divisor, is going to be 4, because anything greater wouldn't go into 8, and anything less than that, well, it would still go into both. So this is going to equal 4, or 2 squared. Where did this 2 squared come from, though? You might notice that both numbers here have a 2 squared in them. This has a 2 squared, this has a 2 squared plus another 2, but still it has a 2 squared. Why couldn't it be 2 to the third? Is because if it was 2 to the third, it wouldn't be a factor of this first number. So what we're getting at really is that the exponents here, you're taking the greatest one that's in both. Because if you take the greatest exponent in both, you're both, lots of boths, but if you take the greatest exponent of both numbers, you're satisfying two properties. First is that you're less than this number here for both numbers, so you're not going over what the factor is here, how high it can go, but also you're going as high as you can. So we have 2 squared, and really we could write this as 2 squared, and then 3 to the 0. Each one has a 3 to the 0, so let's write out the 3 to the 0. And then this one has a 5 to the power of 1, but this 2 cubed times 5 to the 0, it has no powers of 5, so we can't take any powers of 5, so 5 to the 0. Let's do just one more example, and we can do it faster because we've got the idea. GCD of 2 to the 4th times 3 to the 0 times 5 to the 1 times 7 to the 4th also. GCD that with 2 cubed times 3 to the 9th, 5 squared, and 7 to the 1. What's this going to be? Well, we need to say there are going to be 3 powers of 2 in this. We can't say 4 powers of 2 because then it wouldn't be a factor of this number. And so 3 is the biggest that we can go with, so we're going to say 3 powers of 2. As for powers of 3, even though we have 9 powers of 3 right here, we have none here. So any powers of 3 would make this number not have a factor there. So we need 3 to the power of 0. As for powers of 5, we see a power of 5 here once and then twice here. And once is the most we can do, because if we did it twice, it wouldn't be a factor right here. So we need 5 to the power of 1. And then the 7s, we have a 4 and 1. So we're going to have to pick 1, because if we picked anything higher than 1, say 7 squared, then it would no longer be possible for it to be a factor of this second number. So maybe now you're seeing where I'm going with this. Because if we need this GCD of this big multiplication of exponents, 2 to the a, 3 to the b, 5 to the c, 7 to the d, 11 to the e, to equal very specifically after GCD'd with 2 squared, 3 squared, 11 to the 1, 2 squared times 3 to the 1, we have some properties that we're going to need to satisfy, some constraints. First and foremost, clearly, we have a power of 2 here, and we have a power of 2 here, and we have a power of 2 here. So at the end, if you remember, the greatest possible power of 2 that fits into both of these is going to have to equal 2. So, right off the bat, we know that a cannot be 0, for example. If a was 0, we couldn't have any powers of 2 here, so it would be impossible to get to the 2 squared. So, a specifically has to be at least 2, because if a is 2, then clearly you're going to get a power of a to pass through. And if a was 3, then you would have GCD of just the powers of 2. You'd get 2 cubed and then 2 squared. And then you're taking the minimum here, the smallest, biggest one. So the extra power of 2 here won't matter because the power of 2 here limits it, so you're just going to get back to 2 squared. Because the GCD of 8 and 4 is just 4. So really, what we're looking at here is that a has to be greater than or equal to 2. Of course, its old constraint also applies, so a has to be less than or equal to 8. But anywhere in between doesn't really matter. A can be 4 or 5, 7, any of them. Just greater than or equal to 2 and less than or equal to 8. The powers of b are a little bit more restricted. You might say, well, great. You see here we have a power of 1. Maybe I can be anything greater than 1. But actually not quite. Because let's consider first, b cannot be equal to 0. Because if b was 0, then no powers of 3 would go through, and then we would be incorrect here. But luckily for us, there's a power of 3 here. So if b has a power of 1, it'll go through exactly to get the 3 to the 1. So the GCD of 3 to the 1 times 3 squared. This is going to be 3 to the 1, which is just what we want on this 3 to the 1. And just so that I'm not confusing you, I am splitting this up by each of these parts of the product, but we can deal with them independently here as we're reasoning through it. Unfortunately, though, let's say I wanted the GCD of 3 squared times 3 squared. This would be 3 squared. So it wouldn't match up with this 3 to the 1. This is the first case where it's happened, but it's possible for us to go too high. And because we have an extra power of 3 here, we actually can't say that 3 can be equal to 2, because if it was, an extra power of 3 would creep through and mess up this power of 3, which must equal 1. So that tells us that b has to not be 0, not be 3, or 2. It must be equal exactly to 1. Alright, for c, notice, we don't have any powers of 5 here. I could rewrite this as 2 squared, 3 to the 1, 5 to the 0, 7 to the 0, 11 to the 0. I'm going to go through this logic a little bit faster now, but it should be fine. We don't have any powers of 5 in the answer, but nor do we have a power of 5 in the second number. So whatever the c is, it's always going to be limited by here, because this is times 5 to the 0 times 7 to the 0, right? This, even if we had the GCD of 5 to the 4th and 5 to the 0, this 5 to the 4th could be anything. It'd be 5 to the 10,000. It would still equal 5 to the 0 because of that term right there. So that's a long way of saying that if you have this power of 5 here, c, and notice also the same exact logic applies to d, because we have no powers over here, but there are no powers in the second term. So c and d are unrestricted. And when I say unrestricted, I mean with respect to our new constraints, they must still clearly have c greater than or equal to 0 and less than 2, and d between 0 and 1 also. But they're unrestricted with respect to these new GCD constraints. Finally, e is our only option remaining here, our only power left to be dealt with. And we see we have 11 to the e and then 11 to the 1. But we can't have any powers of 11 here. Because we can't have any powers of 11 in the answer, and we have a power of 11 here, we say, well, if we had any powers of 11 here, they would go through. So for example, the GCD of 11 squared and 11 to the 1, this is going to equal 11 to the 1, and that disqualifies this because we can't have any powers of 11 here. So because we can't have any powers of 11 in this first one, because any power of 11 greater than 0 would sneak through this one and go to the answer, and we can't have that, we get that our 11 here, our e, must be equal precisely to 0. This is interesting. What we did is we said for every single factor, I can generate every factor, but now I'm telling you out of this factor generation machine that we made, I have a recipe for you to make any factor that you want, such that the GCD of that factor with 2 squared, 3 squared times 11, 396, is equal to 12. I was about to say 0, but no, it's equal to 12. And given this recipe for factors and now these constraints, we can say, well, given these constraints, I know before I had 540 factors, how many factors satisfy these constraints? Well, let's look at the constraints one by one. We're saying that a must be either, so a is greater than or equal to, less than or equal to 8. That means a is either 2, 3, 4, could be 5, 6, 7, or 8. And then b is definitely 1, because again, we can't have any powers of 3 sneaking in. More than 1 at least. C and D are unrestricted, and what that means is that C is unrestricted with respect to the new constraints, but still between 0 and 2. So C is 0, 1, or 2. D is similarly, we have between 0 and 1. D is 0 or 1. And E is precisely 0, so that no powers of 11 sneak through the GCD. And now let's look at our options. Right here, this is equivalent to saying we have 1, 2, 3, 4, 5, 6, 7 options. Interesting. 7 options. Here, on the power of b, we just have 1 option. Just has to equal 1. Here, on c, we have 3 options. I'll stop writing option. On D we have 2 options, and on E we have 1 option. Whenever we have options, we say, well, I have 7 options here, 1 option here, 3 options here, 2 options here, 1 option here. We can multiply them together to get how many total choices we have. Because if I have 3 choices here, and then I make another 4 choices here, that's just multiplication. And if you take all that and say, all right, make another choice here, that's just, again, multiplication. So what I'm saying is our total options. So total options is going to equal 7 times 1 option times, great, 3 options, cool, 2 options times, only 1 option. What is this? This is going to equal 7 times 3 is, well, 7 times 1 is 7, times 3 is 21, times 2 is 42, times 1 is 42. 42. And when we say 42, we specifically mean that there are 42 factors of 11 factorial that satisfy GCD of whatever that factor is with 396 equals 12. By using our generating formula for these different factors and combining it with what we know about the GCD for prime factorizations, we're able to find our answer. It's 42, the answer to the life, universe, and apparently this problem. I'll see you in the next video.